great pleasure to have Pastor Levin's last lecture, and as usual, if you have any questions, just interact, and we'll be happy to answer them.
Thank you, Laszlo. So let me remind you of what we said yesterday. So yesterday we discussed ISTA, which means local density approximation, which means that you think of, so you give yourself a density, and then you think of your gas as locally constant, and locally you replace by the energy of an infinite gas, which has constant density everywhere, times the local volume. Okay, so the state one was that the F of rho was approximately equal. So you always have to put the Coulomb energy, which is non-local. This is for Coulomb. Txt1, so that's Coulomb. And then you have a local term which was called integral f of rho of x dx are free, and then there was some error terms. That's the LDA. And so you, what is f? And so f is really the energy per unit volume, f of rho. Volume of an infinite gas of electrons having constant density, and to which you subtracted the director. Constant density rho with the direct subtract. Okay, so some people call it the indirect energy when you look at the energy you subtract the direct term, the indirect energy. And so this F is very important because you see it's the central object in DFT, it's the kind of the first big approximation you can do. But actually this system, so infinite gas of electrons at constant density, is a very important reference system. Okay, so now I'm going to really discuss the uniform electron gas. Because it's the central object in DFT, or one important object in DFT. So somehow it's a reference system, okay, a little bit an easier system because it's translation invariant, it's infinite, and which is used as a reference for DFT calculation. And so it's going to be a slightly different topic today in the sense that we do much more statistical mechanics. There won't be too much DFT in a way, but that's the main system of DFT. So I'm going to talk about this UEG, uniform electron gas. One reason I want to talk about it also is because it was very lively in the past 10 years or so in this subject. In particular, there were a lot of confusions and controversy even, because if you go to Wikipedia and you look for uniform electron gas, you will realize that physicists and chemists, it's not that they make the confusion, but they decided that several models that look different are actually the same. And so if you go to on Wikipedia, the page is the same for what's called helium, and which is also what's called the homogeneous electron gas or uniform electron gas. And for physicists and chemists, it's just the same. And when we were studying this problem with Elliot and Robert, it was natural to introduce this uniform electron gas defined that way, namely an infinite gas of electrons at constant density, and it was not clear to us if it's the same as helium. And when we tried to prove that they are the same, we failed. So we had a lot of discussions with chemists and physicists. We asked them, why do you think they are the same? Then first they said, we never claim they are the same. Then they said, yeah, well, you wrote it, yeah, but it's not the name, but of course they are the same, but maybe it's... anyway, so there were a lot of confusions, and it took a few years before finally we could prove they are the same. And so share with you. So I want to define these two models and then explain why it's difficult to show they are the same. And I'm not going to do too much details, it's maybe going to be more of a review. And this is really some very important model in physics, not only for DFT, it appears in many situations. Okay, and so I'm going to discuss the UEG and the leak with Jelium, and everything I'm going to tell you is in a long review paper that I wrote recently, which is called Coulomb and ISTA series. And it has appeared in JMP in 2022. This paper also has a long history. It was really a pain. It's a review paper. So I decided to write this paper because there were many talks by many people who had the Coulomb gas. And it seemed to me that everybody was ignoring what the others were doing. So I thought that this must all be the same thing, but everybody had a different definition, and it was really not clear to me whether the definitions were really the same, which is the problem we were having here, in a way. Okay? And so I decided to look a little bit more closely at the literature. I did that in 2017, and after several months of reading papers, I gave up. Because I just couldn't understand. Everybody had a different definition. They were never comparing. When I was discussing with them, they said, "Oh, they did not." Anyway, so I gave up. And then in 22, I said, "Okay." So I was invited to write a paper for a special edition of JMP in honor of Freeman Dyson, who also played a big role in this business, in particular concerning random matrices, where there is also a kind of Coulomb gas. And so I said, okay, let's go back to this. And so it took me really a long time, many months. In the end, this review is like almost 100 pages, and it has more than 500 references. Don't ask me details, I read them all, but I've forgotten most of them. But, and each time I have to remember, I have to read my own review, but I don't remember. But anyway, so everything I'm going to tell you today is in this review paper. So, so the UEG, I've given the definition to you. What is Jelium? Maybe I make some drawings. So maybe I write a sentence and I make two drawings. So Jelium is a little bit different. So what you do, so it's also an infinite gas of electrons. But you do not put any constraint on the density. Constraints on the density are really DFT-like things. So it's an infinite gas of electrons, but living in a uniform background. Of opposite charge. Electrons have negative charge, so of positive charge. So you see, it's not the density of the electrons that's constant, but it's the external potential, which is induced by the constant density. Okay, so the picture is like this. I don't know if I can make a clear picture, but we will try. So Jelium, so you've got a background, there it is, and I'm doing a finite piece, of course, then you're going to take a thermal limit, make it larger and larger to have an infinite gas. Okay, so this is Jelium. So I have this uniform charge, say charge +1, uniform over a very large cube. And then I'm going to minimize the positions. Of course, in quantum mechanics, it's a little bit more complicated, but soon I will do only classical for simplicity. So think classically. So I'm going to put some electrons, okay? Here they are. The blue guys, so I put n electrons, and I just minimize over the position of these n electrons in this fixed positive charge density. I put as many electrons as the total charge of the nuclei. Okay, so that's the picture. And And so the picture for the UEG is a little bit different because I do not have any external potential. I do not have any external charge, but the picture is, yes.
Minimize doesn't minimize the energy.
Yes, I will define the energy later. But, I mean, if they are quantum, they don't have a fixed position, they move a little bit. But if they are classical, they are going to just minimize the energy and just be clumped where they like. So the UEG is a little bit the same one. So you take a very large cube, and then you ask that the density is constant, so say it's equal to -1. Rho of x, I mean, rho is 1 because we put an e squared, but no talking about. So the density is constant. So now it's the density of the electrons that's constant. So I still have some electrons. There they are. However, my electrons, they do not have a fixed position because I have a probability measure of these n electrons. So they have to move somehow, so I have to think that they move. Okay, so I have a probability measure of these n electrons which is so that in the end the density is exactly constant. And then I minimize the energy. Okay? So I'm going to do everything classical now for simplicity. So of course, for us, it's quantum. Okay, so let me remind you that the f of rho has the following form. I mean, the quantum guy, it behaves, so it's shaped like that. And it behaves like minus constant rho to the 4/3 close to the origin, and then the Thomas Fermi constant rho 5/3 minus the Dirac constant rho 4/3 for large densities, you remember? And it turns out that the classical regime is here. So at very low density. Okay, so that's because the kinetic energy is like rho 5/3 and the Coulomb energy is like rho 4/3. Okay, so when rho is very large, the kinetic energy wins. When rho is very small, the classical energy wins. And so at very low density, I actually get the classical gas. And today I'm only going to discuss the classical gas, so I will mainly concentrate on that constant C. Very good. So let me now define these two models classically. You can do the same quantum mechanically, but then less things are moved. And probably everything that I'm going to tell you is true for in quantum mechanics, but it's even harder to do. So, okay. And in order to understand why it's difficult to compare these models, it's very useful to not only look at Coulomb. Because it turns out that Coulomb is a little bit critical in this business. And so to understand why it's difficult, it's better to look at a wider range of interactions. And then in this class, we will see what's special about Coulomb. Okay, so I'm going to look at these interactions. What are these interactions? So it's just that I'm taking W of x, which is 1 over s to the s when s is positive. So for Coulomb, it's just s equals 1 in 3D. And you see, I will given a low negative s. So if s is equal to 0, what I do is I just expand for small s this thing. Okay? When s is 0, I get 1, but I am not going to take the interaction equal to 1. So I look at the next order, so I put minus log for s equal to 0. And it turns out that for negative s, it's natural to switch the sign. So if you switch the sign for negative s, somehow let me write it like that. So this is going to be the Riesz interaction. And of course the 3D Coulomb corresponds to s equals 1. Okay. But actually, so in general, the Coulomb case is s equals t minus 2. Okay, so we will call Coulomb. I mean, if you talk to a physicist, Coulomb is 1 over x in all dimensions. Because if you have charged particles, they interact with 1 over x. If I put them on a plane, they still interact with 1 over x. If I put them on a we are going to call Coulomb what corresponds to the fundamental solution of the Laplacian, so which is S equals E minus 2 in any dimension D. And so you see that in 1D, it's minus modulus of X. So this kind of Coulomb potential in 1D is a bit strange, because it becomes infinity. In 2D, it's minus log, which is very important. And then it's 1 over X to the T minus 2. Okay? Very good. So this plays an important role. So for instance, so the T equals 1, S equal to 0 is the 1D log gas, which is also sometimes called the Dyson gas. And this plays an important role in the study of random matrices. But actually, the Coulomb case in 2D, so if I look at E equals 2 and S equal to 0, so that's also Coulomb, that plays an important role for the fractional quantum Hall effect. When you look at Laughlin wave functions, then you naturally see this minus log appearing. And it also plays a role when you study vortices of uniform order. And so on and so forth. Anyway, so you see many values of S are interesting. Not all values of S, but to understand the behavior, it's natural to just interpolate and look at all S's, even if some values of S are perhaps less physical. At least we will see what's special with some of these values. Okay, so let me now define the energy and discuss the existence of thermodynamic limit. And for this lecture today, I'm going to really look at the simplest problem. I'm not going to put any temperature. I'm not going to put any quantum. So it's really the easiest. So I'm just minimizing the positions of my particles. And I will first discuss Jedium. So I will look at Jedium model for any S. So what is it? So I have a domain omega, which was a cube over there. So I have a domain omega. And then I have a certain density, I call it rho 0. You will soon realize that rho doesn't matter, it is equal to 1. Rho 0 is a constant, it's my uniform background in omega. And then I put my n particles in there, and so I have an energy which is, so let me call it E of omega rho 0 of x1 and xn. So that's the sum. And let me write 1 over x to the s, because I mean I can write W, but it's better if you see. Of course, when s is 0, you have to replace it by the W. It's perhaps you want me to write W. So let me write W of xj minus xk. So that's the interaction between my n particles. Then I have to put the interaction between the particles and the background. Okay, so that's minus the sum j into 1 to n, and then I have rho 0, and then the integral over the background of w of xj minus y to 1. Okay, so the background generates a potential which is this thing. Then I sum over my n particles. That's the energy. And then it's very natural to add a constant. Somebody complained when Aspiron wrote this, so let me do the same. So we add a constant. Just to make the energy of the order of the volume, we need to add a constant that does not behave like a volume, which is the self-energy of the background. So it's rho 0 squared divided by 2, and then integral over omega, w of x minus y dx squared. Okay, Okay, so that's the J-term energy of n point living in the background. And now we optimize. Okay, so we just minimize this stuff. So let me call En of omega rho 0. So that's the minimum with x1, xn. Let's assume there are an omega of this energy. So we minimize all the positions of the n points. Okay? And the theorem is that the thermodynamic limit exists. So if I make omega grow and I make n grow at the same speed, if you like, then the energy per unit volume will converge to something which is going to be related there. So, now let me give you. So I will take a sequence omega n which grows. Okay, let me be a bit vague here. I mean, you need some constraints on this omega n, but think of a sequence of poles, the center, at the origin, or fused. It's just important that it doesn't depend on the shape of omega n, it doesn't depend too much. But if you take a very wide omega n, it might not work. So let me just take a very smooth sequence of omega n's. For instance, you take an ISTA that you scale. And then I will assume, well, so then, I mean, there will be 2 points in my theorem. So first, I will assume that the system is neutral, okay, which is called the Canonical case. So I will assume that I also have a sequence of n, of course. I assume, if you like, that n is equal, or actually I mean n divided by omega. You assume that n is equal to rho 0 times omega n. Okay. And then the statement is that if S is between the max of 0 and t minus 2 and t, and in 1t, I can also take S to t minus 1. Okay. Then the energy per unit volume converges. So I have E of omega n 0 divided by omega n converges to a constant, which so that's the energy per unit volume of the J-term gas, the risk gas, if you like, that depends on S. And there's an obvious scaling here because my W has an obvious scaling. So actually, I could also take rho equal to 1, but then you can get rho 0 to the 1 plus S. Okay, just by scaling, that's the rho 4/3 I was discussing in case of 2. And if S is equal to 0, I mean, for S equals 0, there's always a log floating around. So there will be a minus rho log rho over 2d log S equals 0. Okay? So this is saying if you have an infinite gas, then the energy per unit volume is something like rho 4/3, so rho to the 1 plus S over d times a certain constant, okay, universal constant that does not depend on the way you did the limit. So it does not depend on the shape of omega n. And that's the result. So now you may complain, you may say, well, why did I impose that it's neutral? And it's actually not needed. However, it's needed if S, so notice that S can be 0, right? So if in dimension 1 and 2, S is allowed to be 0, which is the Dyson gas and the Coulomb problem in 2D. And in dimension 1, you can even take S equals minus 1. And there it's very important that it's exactly neutral. So it's actually, so if S is strictly positive. Then you can, you don't have to fix n. So what I'm going to say, I'm going to state something of grand canonical nature. Let's just minimize over n. Let's take the best n. Why not? So you have the same results. We have the minimum over n of the same en divided by the volume that converges to E, G, S, 0, 1 plus S over T. And actually, you can also show that if I call, let me make remarks. So for the second limit, if I call n the minimal number of points you want to take, then this guy will actually behave. It will be essentially neutral. Okay, so this divided by omega n has to converge to 0. If n is the R-mean of the En of omega n over 0. Okay, so it wants to be neutral. Why does it want to be neutral? That's because these are very long-range potentials. Right? So when S is less than the dimension, which is what we are looking at, then your function is not too singular at the origin, but it decays very slowly. It's not inseparable. And so each particle sees a lot of neighbors very far away. And so you have to prove that there are some cancellations, otherwise nothing will work. And actually, if you do not put any background, everything will collapse to the boundary. And so the background which we've put here is to make sure that the particles, hate each other less, make sure they can live together and form a macroscopic object. And so everything is about understanding these problems due to the long-range nature of the interaction potential. Very good questions about this theorem. Is it clear? No? Okay. So history. So you see already that we have two different limits. This limit here and this limit there. And already we see differences. So the first limit was proved, but never going below d-2. So in dimension 3, it's stuck at 1. But the second limit is true for all positive S, if you minimize over n. Okay? And the statement is that the limits are the same whenever they exist. No, the statement is not that. The statement is the limits are the same for both S. And so now it depends whether you first prove one and then get the other, or it depends which way you go. So history, this was proved first for the Coulomb case by Lewin and Marmolfer in 75 using some previous works by Lewin for Coulomb. And they proved actually both limits. And they proved that they coincide. Then this was generalized for S equals d-2 in dimension, I think 2 and higher by Sarri and Bernini, which was 76. And actually the case S equals -1, d equals 1 was done by Kunz, which I think was 74. So these are all the Coulomb cases. So for Coulomb, you have Newton's theorem, which is used a lot in these proofs to get the result. Then, so there's a very long series of works for the canonical problem. So this I call canonical, this I call grand canonical, because here I don't fix the number of points. Okay, so the canonical problem was studied by Serfati with many people. So first it was done with Sandier in 2D for Coulomb, so for the log. Then usually for Coulomb in any dimension. And then with the Petrarch for general S in any dimension. And then it was revised with Armstrong more recently. So this all goes over a period which is 2015 up to 21. Okay, so many results. So actually, when you read the first paper, it's not clear that they prove this theorem because they have a different definition. They look at a different problem. And they look at a problem where you have an external potential which is not of the kind I hoped. Okay, however, if you look at the last paper, the one with Armstrong, then you realize by looking at the proof that they actually prove this. Okay? Very good. And this is only about the first limit. So now if you discuss the grand canonical problem for which the limit exists for a larger set of values of S, then I have to cite first Pfefferman in 1985, who gave a different proof of the S equals 1 equals 3. That was grand canonical. Okay, so it's a different proof. I mean, he did much. It's completely different. It's for a periodic system, but of course, constant is periodic. Okay. So he gave a different proof of this, okay, if you like. But more importantly, then some students, in particular Gray, in 1989, so they could do the grand canonical for all S between 0 and D by following the proof that Pfefferman had found in the periodic. Okay, so that's this limit here. It follows from these papers. In 2009, we also studied this problem with Christian Heinzel and Jan Philipp Solovay. And we came back, so we gave a third proof, if you like, of the case S equals 1 in dimension 3, using an inequality of Graf and Schenker on 85, which allows to quantify a little bit the kind of screening that you can have in such an infinite class. And now the question arises, imagine you can prove this limit. Does it imply that limit? Because here you minimize the line. Okay, so it's not so clear. Does it imply? So is the grand canonical really implying? Usually canonical and grand canonical are the same. If you can do one of the two, then you get the other one. Okay. But here it's long range, it's not so easy. And so actually, so in my review paper, I wrote the proof that that GC implies C, if you like. Yes.
Yes, sorry. A question about the remark over there. So you're minimizing with respect to N, and any idea this and the remark?
The remark is that so when you minimize, there is a certain minimizer N, then it's almost neutral. But maybe not exactly. We don't know. I mean, it's always easier when you minimize over N and don't care and allow the number of points to vary. The proof is always easier to do. And one consequence is that we can do it for a larger range of S. However, when S is negative, it has to be neutral because the interaction diverges, so it's equal. Okay, so this is saying, and it's almost neutral, but maybe not exactly. So here you have more constraints in a way, so this limit is more complicated, if you like. So, but usually it's the same, you do one or the other and they are the same, and so in my review paper I prove that if you know how to do the limit GC, then you get the limit C with the same constant. choices. You can start with this and then deduce this, or the other way around. But before, the link was not clear. So there were several theorems, but nobody was telling you that the constants were the same, which was a little bit awkward. You see that so there's a clear open problem. What is happening in the canonical case for S less than t minus 2, and I have no clue. So we have different proofs, and they all break down when we pass Coulomb. So Coulomb really looks critical. So the proof I gave here, so the grand canonical proof works for all S between 0 and t, so between 0 and 3, if you like, but at 1, I cannot prove that this limit here exists and is given by the same constant, below 1. And then Serfati and co-workers, when they study this here, they are stuck at t minus 2 because they used this Caffarelli-Silvestre extension, which requires the power of the Laplacian to be less than 1. Anyway, so they are stuck at t minus 2 because of the method they use. Yes?
To clarify, the first line you wrote, you said this applies to S equal to t minus 2.
Yes. Exactly. Yes. Okay, so that's what's known concerning this helium, this whatever gas. Just the energy per unit volume, the convergence in the thermodynamic. Now let me look at the second model. So let me now look at the UEG. So the UEG, we studied it with Elliott Robert, the classical back in 2018. And so what's the statement? So let me introduce, so now I'm going to introduce the lowest energy you can reach and the constant when the density is constant. Okay, so let me introduce the classical equivalent of our F. Okay, so C of rho is going to be the minimum over all n particle probabilities, okay, so probabilities, symmetric probabilities of the endpoints with density rho of the integral of the sum of SJ minus SJ yes, dp. Okay? Over RT to the end. Okay, so that's it's just the lowest energy you can reach, right, if you fix the one particle density. And this here is really a much marginal optimal transport problem. And because this P, you're actually fixing all the marginals because they are all equal because P is symmetric. Which, by the way, does not play a role for the theorem I'm going to state, but we used some results coming from optimal transport in some other places. Anyway, so what's the theorem? So the theorem is the following. So now you take S between 0 and D. And the limit exists. Okay? So you look at the cost, so you take rho 0 times the characteristic function of the set omega n. So you assume that you have a constant density of a domain omega n. Okay. You remove the direct term, that's rho 0 squared divided by 2 omega n, and then dx dy divided by x minus y ds. You divide everything by the volume, and the theorem is that this converges to a certain constant, E UEG, less times rho 0 to the 1 plus S of t. Okay. So one first remark is that there is a similar result if you do it grand canonically. So if you start minimizing, not minimizing, but you look at the C bar, you remember Umberto, there was an F bar, so same, the C bar, so when you take a collection of Pn and so on, so that's the grand canonical version. I'm not going to state. Same with the same limit and so on and so forth. And so here, the situation is different from the Gilliam case. Namely, we have a kind of canonical problem. So the number of points is fixed here, right, because it's the integral of 4, 0. And we also have a grand canonical problem. They coincide, the density is fixed, and it works for all S between 0 and D. And I want to emphasize that the proof here is much easier. Much easier than the other proofs. The fact that you know the density tells you that the particles, they can't do anything bad. Because you know, in any given volume, you have a finite number of guys in that batch. Okay? So somehow they must scream the way they are. You don't care what they do, they must scream because you know the number of points per unit volume is fixed. So the proof is much easier. We just prove that the energy is subadditive, and then we use usual methods, LREL. Usual methods in statistical mechanics to conclude that the limit exists. Okay, very good. And so if I go back to the F over there, okay, so here I'm fixing the density, and so of course this model here is the one related to the ellipse, to the LTA. So if I go back to ADA, then the F of rho of yesterday is actually equivalent to the EUG of 1 rho to the 4th term when you are in dimension 3 and S is equal to 1. So the constant of the LDA function F at the origin is this energy. And so physicists and chemists, they always said that this constant must be the same as the other constant, because they were always confusing the two models. For them, UEG is the same as JM. But I mean, both are kind of homogeneous in a way. But JM, doesn't look very homogeneous, because the points they will sit somewhere. So they were always confusing the two. And so here they would put the other constant for which there is a very famous conjecture due to Wigner. Okay. And so the question is, what's the link between the two? And so in a paper with Lead in 15, we tried to prove they are the same. And we failed. We thought it must be easy. And then when we wrote it, it was not working, so we started to talk to physicists, and it was completely unclear for a while. So actually, we realized that the proof should work if you are above Coulomb. But at Coulomb, there was a problem. This is what I'm going to explain later. Okay, so problem for S equals -2. And finally, this was a result, and so the theorem is the following. And it says that for all S between D-2 and D, probably, yes, exactly, I think that's correct. Maybe I should write the max of 0 and D-2, okay? The one, so I'm not talking about 1D. So in 2D, D-2 is 0. Okay. The statement is that the two are the same. And D-2 is included, which was the difficult part. so let me remark that the theorem is wrong in one thing. So if you take S equals minus 1 in dimension 1, then the two are different, you can actually compute them. So the J-ion energy was computed by, was probably known, but at least returned explicitly in the paper by Kunz. So the E J-ion of minus 1, if you compute it, you find 1 over 12. And then there is a nice paper by Colombo Di Marino and Pascali in 15, where they studied general multi-marginal optimal transport problems in 1D. And in the case where rho is a constant like here, they could solve it exactly. And then if you apply this for the Coulomb cost, you conclude that the E unit of minus 1 is actually 1 over 6. Okay? So the theorem cannot be always true. Maybe for S negative, but this, and then, so then we did, so it's the first thing, Cotard, big crash. The first to solve the problem in 19. They wrote a very, very long paper of about 60 pages, very technical, to prove that they are equal. So actually the way they did it, so the theorem was kind of easy when S is strictly bigger than D minus 2, and they proved that it's a continuous function. Okay, so they managed to show it's continuous and go back to S equals D minus 2. Very good proof, and then we found a much easier proof a few months later the same year, which was quickly outlined by Aspion. When was that? Tuesday? Yes. And which I will also quickly outline if I have time at the very end of the lecture. So simpler proof, say 2 pages. And actually, Aspion was also, what was that, 21. So looked at the missing case. I mean, we never really considered the log. So he looked at the 2 digits. Okay. Very good. And so, again, we are stuck, you see. We are stuck at D minus 2. But I don't think that this result is wrong below D minus 2. It's just that the way we do the proof relies on results by Serfati and co-workers where they are stuck at D minus 2. Okay, so maybe one remark is that for the proof, we compare energies with a third model. Too many models. No? So we compare it with a third model, which corresponds to putting particles on a torus with a periodic interaction. Okay? And so there is a third guy, which is the E periodic of S, and for which the thermodynamic limit, I'm not going to define it, it's very easy, right? So you work on the torus, no background, nothing, but you look at the interaction whose Fourier coefficients are 1 over k to the s. Okay, discrete. And the Fourier coefficient at 0, you take it to 0, for instance. So this guy, the thermodynamic limit, exists for all S between minus 1 and D in any dimension. And actually even minus 2 and 1 in dimension 1. So it's even more confusing, you see. periodic system makes sense for a much larger range of SEs in the canonical case in all dimensions than the other ones, but we can compare them with the other ones only when S is above t minus 2. Too many models. Okay. Very good. So now I want to do two things for the remaining part of the talks, but I guess I will do maybe one thing. I will first discuss the conjecture value of that E, which is related to the crystallization conjecture. And then, if I have time, I may have no time, but you've learned everything already with Asbjørn, explain to you why what I will be talking about is related to the problem about showing the result at S equals Z minus 2. Okay, so now I discuss minimizers. The crystallization conjecture. Okay, and I want to explain why we have to put this back on. I will mainly discuss the EJM. Yes, at the very end, if I have time, I will tell you a few words about UEG. Okay, so maybe, if you first assume that S is bigger than D, then your interaction is short range, it's very nice, and so everything is very nice. But and then we can compute Z. Okay, but let me first tell you that Wigner in 34 conjecture that Gelium is crystallized. And so, sorry, he did that for the Coulomb case, and he conjectured that it's crystallized on the PCC lattice. And so the question we ask if it's true, or what is the value of the constant, and what is it that we have to prove. And to understand the situation, it's better to first assume S is bigger than T, and then we put particles on the lattice. N, okay, now so there is the lattice, put the particles on the lattice, and then you compute the sum J less than K less than N of 1 over Xj minus Xk to the S. Okay? And you put them on a lattice, you do the thermodynamic limits, you take a huge domain, only keep the particles in the domain, So if you divide by the volume, and let's assume that the lattice has one particle per unit volume, then we don't have to worry about rho. Okay, so let me assume that the unit cell, let me call it Q. Okay, so it's easier to put the particles in the middle instead of putting them in the edges. So it's like that, and this is Q. It's the unit cell. So and let me assume that Q has volume 1, so that I have exactly 1 point per unit volume. And then, so if you do 1 over omega n, and then the sum of 1 over maybe like Z minus Z prime, yes, Z defined from Z prime and Z prime in omega n intersected with the lattice, okay? So that's what you have to do. I have to put a factor of 2 if I write Z minus Z prime, because I don't want to count it twice. Then you see this converges to 1/2 the sum Z in the lattice of 1 over Z to the power S, and Z different from 0. Okay, because you look at Z minus prime, and then essentially any Z sees every one more or less, and then the number of Z's is the volume. And so this function here is what's called the zeta to any dimension and any lattice of the usual Riemann in the term. And the small lemma is that this theta L over S for any lattice has a meromorphic continuation C with a unit pole at S equals D. Okay. So it's a little bit funny in a way, so you can define the interaction in the short range case, and then you can analytically continue to the left. And then we ask ourselves, is there a link with what we've been doing here? So to see the link, then we take S less than T. And now we put a background, because of course we have to. So we take the same lattice S. There are points. Okay, then you take, say, a ball or something. Like that. So let's say this is a big ball, or any omega n, let's say a big ball beta. Okay, and now you will just stick the points in a big ball of your lattice, and then you need to define a background. So what you do is, as a background, you take the union of the cells of the corresponding points. Okay, so the background is not the ball, it's the union of the cells. It's a little bit easier. Okay, so I take capital XR, it's just L intersected with BR, and then my background omega R is the union of the Z plus Q, Z in XR. And then the small lemma, which as Bjorn stated on Tuesday, is that when you compute the Jaeger energy, so the E n, how would you call it? Omega R, rho is 1, okay, and then XR divided by the volume, so that guy over there, okay. So now you do the thermodynamic limit, this converges. Okay, so now you're computing the Jaeger energy with the background of a lattice. So I take a piece of the lattice, I take a background that goes exactly around, contains exactly a union of unit cells, and then the theorem is that you get zeta L of S. So namely, putting the background is the same as doing an analytic continuation in S. And this works for actually the mass of T minus 4 and minus 2 S in T. And I mean, of course, when S is 0 or negative, it's not exactly zeta. Okay, let me not practice. So you get minus zeta if S is negative, and you get zeta prime if S is equal to 0. Okay. So that's the lemma. So the message is that the background is just doing an analytic continuation. So in a way, if you knew everything about your system in the long range, in the short range situation, then you know a lot in the long range just by doing analytic continuation. And these are ways that actually physicists, I mean, they don't really say it's analytic continuation, but the formulas they write actually tell you that you can compute by writing everything in terms of the large S. Okay. So the conjecture now is that the E, so the conjecture I volume 1, okay, of this H times zeta. Okay, so it says that the system is crystallized. And you just have to find the optimal lattice. And there are also conjectures about what the optimal lattice must be. And the conjecture is vague because I don't know for which dimension and I don't know for which S, because it's a conjecture. I can be more precise in 1, 2, and 3D, but not so much for any. People say that in very, very high dimensions, it's unlikely that you're crystallized. I don't quite know. Okay? So this conjecture is known and has been proved in dimension 1 for all S. So now let me not get confused. For all S. 0 and 1. Actually also S equals minus 1. I think it's not in return between minus 1 and 0, but I think it's true. No problem. This was done by Roger Mischbauer in 79. And then there are two other cases that are known, which are dimension 8 and 24, and S between B minus 2 and B. And this is actually the result by Rainer Zowska. In 21, I think, or 22, for which she got the Fields medal. Actually, she never really looked at the problem of S less than D. Okay, she proved the theorem for S bigger than D, that it is crystallized on a certain lattice depending on the dimension. And then there was a paper by Petrasch and Serfati where they explained that what they had done for S bigger than D actually implies the theorem up to D minus 2. Okay? And so far it's all what's known. And so the conjecture in 3D is that the E genium of 1 must be equal to zeta, so it must be the BCC lattice, as I mentioned yesterday. And then the value would be minus 1.44, which all physicists and chemists are using, or were using, in the LDA function, which is why we were confused. Because for Gelium, this was a famous conjecture, but we didn't know that the UEG was the same, and so this is why we were a little bit confused. Let me finish when we have to finish. 5 minutes. Let me finish with a different lemma, just to explain the problem, which is about the potential. So the whole problem of this story is that although the energy is kind of right, the potential generated by these particles is not right. There is a problem with the potential that's generated by even a lattice or any point. Something is not right, so let me state the lemma, which is the same as this lemma, but for the potential. Okay, so I take a lattice L, and I will assume that the unit cell Q has no further pole. So very symmetric, like BCC. BCC is very symmetric, or QB for BCC or something. And that means that the integral of x transpose dx over Q is a constant times the identity. And that must be IP over T integral x prime dx over Q. Okay? And then I look at the potential now. Not the energy, but the potential. So I take an infinite set of points on this lattice, and I look at the potential that they generate. I look at the sum z in L, 1 over c minus x to the s, where s is bigger than d. Now it's the potential. And this has, again, a neuromorphic extension. C of T. I mean, the potential is not extremely different from the other thing. You see what you do. I mean, you put aside the case z equal to 0, and then you take x equals 0. Then it's the same as the other. Very good. So now I'm asking, do I have the same theorem like as here? So I take the same xr, the same omega r, and I compute the potential they generate. So I compute the following. So I compute the sum z in xr 1 over x minus ds minus the integral over omega r over y x minus y to ds. And then I take the limit when r goes to infinity. Okay, so I am asking, is it also true that when I compute the limit of the potential, you see this background here is used to make the series convergent, because of course when S is less than D, the series is divergent, so the background is here to somehow keep the divergency. That's what we hope. And so the theorem says that this is what you think, namely it is the phi L of F, of X, if S is between D minus 2 and D. But at D minus 2, there's a jump, a sudden jump, which is the measure of the sphere divided by 2D and the integral of x squared into dx over the q when s is D minus 2. Okay, so suddenly, when you take S in the Coulomb case, if you only look at Coulomb, you don't see it in a way. I mean, you see it, but you don't know that it's special. But if you look at all possible values of S, then you see that there is a sudden jump in the potential that's generated by an infinite configuration in an infinite background. And now let me take 1 minute. And this is the reason for all the problems. Because you always have to compute interactions between the points or particles or background, and if your potential has this sudden shift, then nothing is working, and then that's the reason that proving the theorem over there was difficult. But instead of talking again about the floating crystal and so on, because I have 1 minute, I will just tell you why you have this job. Because it's easier to explain. And then I stop. Okay, so let me introduce the following f, which is just 1 over x to the s, minus 1 over x to the s composed with 1q. Then you see your omega r is just a union of the unit cells, so that's exactly what's there. It's exactly 1 over x convolved with 1q. Okay, so what's clear is that the limit will be equal to the sum z over the full lattice of f of x minus z. And if you write everything, once you write this as a sum, and then you put the sum out, okay, you see that this is the limit. This f is a very nice f, so even though this guy is not in L1, you can convince yourself that with the dipole conditions, I forgot to say that Q is always symmetric when you can assume it's symmetric, and then the dipole condition. This f is a nice guy, it is in L1, no problem. Okay, so it is integrable at infinity, so this screens this in an efficient way. Okay? And now we have just a periodic function. Right? So we have this integrable f, and then we take this sum, so what we are doing is just to periodize f over a certain lattice. And so to understand the limit, I can also look at the Fourier coefficients. And the Fourier coefficients are the f hat of k. Okay, so when you have a nice f that you periodize, when you compute the Fourier coefficients of the periodic function, they are just the values of the Fourier transform on the dual lattice. Okay, in the dual lattice to L. Okay, and so I just have to understand the Fourier transform of f, and of course the Fourier transform of f is just a constant 1 minus 1 cube Fourier transform divided by k to the d minus s. And you see, when k is in the dual lattice, then this is actually 0. That's what I used already yesterday. So I only have to look what is the coefficient, the Fourier coefficient at 0. Okay, so I take k to 0 to understand what's the Fourier coefficient at 0, and there I see that something is happening, because you see that the 1 cube of k behaves like 1 minus k squared integral x squared dx over q. That's the term of k squared. If you expand the Fourier at the origin, you just expand into the ikx. Okay? And so this guy is 1 minus order k squared, so the numerator is just order k squared. And so now it's very clear what is happening. When the numerator is smaller than this goes to 0, but when they are exactly of the same power, it doesn't go to 0. So you have this sudden jump that f hat of 0 is equal to 0 if d minus s is less than 2, which is s strictly bigger than d minus 2, and otherwise it's non-zero, and you can compute the limit if s is equal to d minus 2. And that's the reason for this sudden jump in the potential, which then explains why everything is so complicated when you want to compare models, right? Because Coulomb has a different potential, if you like, than what you would expect. So I hope you like DFT even after these 4 hours of DFT. There are many open questions in DFT. I discussed mainly problems of ground states, because there the formulation is very thin. I have to tell you that nothing is known about excited states, nothing is known about the time-dependent DFT, nothing is known about relativistic DFT. So if you want to invest in this direction, do not hesitate. Thank you very much.
Thanks very much for the very nice lectures. Finishing it. So any question? Yeah.
So in any 24 dimension, you quoted this result in the some scale, so I assume it's called the sphere packing?
No. So sphere packing is when s goes to infinity. You see, my W is erased, but when s goes to infinity, right, your potential will be the hardcore, and then that's sphere packing. But they actually studied all values of s above t. I mean, they have this. They actually looked at all. How is it called? Any things that you can write as a Gaussian, as an average of exponentials. Anyway, so they look at the whole class of potentials, and that includes the one who rise to the s or s bigger than t. And they can show that the lattice is the same as for the sphere packing. So they have this concept of universal packing, which is the one for the sphere packing, which also works for all s.
Okay, so it doesn't work with 3 dimensions.
It does not work in 3 dimensions because there's no universal packing. So in 2D there is, it's the triangular or hexagonal, depending on how you call it, a triangular lattice. Okay, so in 2D you expect all the same, but they can't do it. I've never understood why, because I don't understand the proof. But they think that the same result must hold in 2D. 1D is easy because there's just one lattice, so it's very universal. And 3D, there's no universal lattice. In fact, the conjecture is that it must be BCC below 3 halves and FCC above 3 halves. FCC is the guy for the sphere packing, and so it's believed that for large S, it's also the optimal lattice. And at 3 halves, because of some symmetry in S, it must change and go to the dual, which is BCC. so there is a phase transition in S for this helium problem at 3 hours. Okay, so there they have no tool, it seems, when there's no universal lattice. They don't know anything.
Okay, any other question?
It's just a curiosity. Are there any attempts to treat other potentials, such as, for instance, I was thinking about the Yukawa?
Yes, so instead of moving S, you can put Yukawa with the mass and take the mass to 0. And it would be the same. You know, it's easier because now you have a short range potential. Okay, so, but I don't know, I think it's nice because, so the advantage of the risk potential is that it is scaling invariant. It has some scaling. And so you don't have to worry about the density, you can make it equal to 1. Okay? And also since there are several other values of S, where it is long range and it has some physical interest, and somehow varying S sounds natural. But of course, actually physicists, they would more introduce a mass and look at Yukawa and then take the mass to 0. This is how they make computation and how you can compute here, for instance. Yes?
I was just wondering, before you define the interacting potential as the integral kernel of the Laplacian, you mentioned that the physicists do something else, that they just say it's just 1 over x.
Yeah, that's right, yes. So in 2D, you can look at 1 over x, and you should, because charged particles, they interact with 1 over x. And the remark is that you are above, so you are in the region where more is known. Because it is long range, but not as long range as the log. And so that's a situation where it was clearer that the models were the same, right? So now it's d minus 1, not d minus 2. Okay, so Coulomb in 2D, so 1 over x in 2D, is much easier than the log. Nevertheless, the log is also very important when you have vortices. They interact with the log and not with 1 over x, so you should definitely look at both.
Thank you.
Okay. Can you hear? Yes.
Yeah, thank you for your lecture. So, if I understand well, so the density functional theory play important role in the study of the fermionic program, like helium atomic physics. So I'm wondering if it's also play important role in the study of bosonic program.
Yeah, it's a very good question. So it's definitely used in classical systems, so I'm not answering your question, I'm just saying it's you summarized. In classical systems, this is what Peter will explain. There it's not extremely successful, because DFT is successful when you are clever enough to find good functionals. And the problem, the good thing with electrons is that you know their interaction, so you can spend all your life studying these electrons, you know the interaction. But as soon as you go to other systems, the W is more empirical, because maybe you don't know exactly what W is, and then somehow, then it starts to depend too much on the shape of the interaction. So for classical system, I think it works fine, but it's definitely not as successful as for fermionic quantum system, for fermionic systems. And for bosonic systems, of course you can say that hospital ISTA is a kind of TFT, but otherwise I don't think it's been used very much. By putting more correlations or something. I don't know, I've not seen anything, I've never seen anything. So good question. I don't know.
Okay, any more? Okay, let's not declare the last time for speaker again, but